randomness mergers. So you can think of this as a toy example of an extractor. So it's a randomness merger. So say I give you two random variables on n bits. And my guarantee to you is that one of them is uniform and the other is, I don't know anything about it. It may depend on on the other random variable. It may not. It may have extra randomness of its own. Who knows? But one of them is uniform, right? So, for the thing, we are going to assume that X is uniform, but we don't know that. We are going to do something which is completely symmetric, so that's fine. But just to keep the language simpler, let's assume that X is the uniform one. But Y can be arbitrarily correlated with X. And your goal is to kind of smash them together, to merge them into one random variable, which is uniform or close to uniform. That's the end goal. Here we are going to have a slightly more modest goal because it's cleaner that way. I just want to output another n-bit string using this from this X and Y, which has a lot of entropy. Okay, so a merger, that's also the way it's sometimes defined, by the way. A merger, it's not just me trying to clean up the definition or the construction or whatever, is a function. Let's call it merge. Let's call it merger. It gets two n bits, like two samples. And let me just, kill the suspense. It also gets a seed. It cannot work without a seed, despite the structure. And it should output an n-bit string also, with the property that if one of X and Y is uniform, then you want that the merger applied to X, Y, a uniform seed. So S is uniform and independent of the joint distribution of X and Y, right? You want this to be epsilon close, epsilon is a parameter, to not uniform, but to some case source. Right, so that's kind of our informal notation, but I mean that, this random variable, you can move it a little bit. So there is epsilon away from it. There is a distribution which has mean entropy, at least K. Okay? So for example, even without a seed, I can immediately get K equals 1/2, like n over 2. Right? Because you can just take X and Y and take the first n over 2 bits of X and first n 2 over bits of Y, concatenate them, it will have mean entropy n over 2, right? Due to the n over 2 bits which are uniform. So really the question is, can you go beyond, above n over 2? So let me write K as 1 minus alpha n, and can you do it with alpha which is smaller than 1/2, right? Hopefully any alpha which is smaller than 1/2, like, and things will deteriorate with alpha, but I do want to support any amount of entropy that I'm being asked to output. Okay. So yeah, so it has this problem has a very nice history, but again, fortunately, I won't have too much time to spend on it, and I'm just going to tell you the construction. So what we will see is a construction in which you can support any alpha with seed length, which is roughly so up to order. So it has 1 over alpha. It has 1 over dependence on alpha times log n over epsilon. And this is quite remarkable. It has a non-optimal dependence on alpha, but it has a good dependence on epsilon, like an optimal dependence on epsilon, up to the fact that you have the alpha here. And it seems to have the right dependence on n, because you see a log n, you're happy usually. Turns out that there is no dependence on n at all in the optimal construction. And we also know construction, explicit construction, that don't have this dependency. And it may look weird a little bit at the beginning, because how can you not depend on n? Well, it may look weirder if you know that seeded extractors do depend on log n, and then it looks weird in contrast. But I don't know. And the reason it doesn't depend on n, like intuitively, is that any prefix looks the same. Still, if this is x and this is y, every prefix still has the property that it's uniform and then some junk depending on that uniform bits. So, and okay, so maybe it makes it clearer. Okay, so how do you do that? So in one way you can try to do, and it actually is useful, but not in this context, is to try to break the correlation between x and y somehow. But then you can show that you cannot output more than n over 2 random bits. So the thing you need to do actually is not to break the correlation. You need to somehow merge these random variables despite their correlations. Okay. So, and this is how we are going to do this. So this is the construction. So the first thing we are going to do is we're going to stop working with 0, 1 to the n, and we are going to we need a field, a larger field. So we are going to identify 0, 1 to the n with fq to the l. So q is going to be some parameter that we will figure out as we go, because I don't really remember its size. And L is just going to be what it needs to be. So L log Q is N, right? To the base 2, I mean. Okay, so you should think of Q as like a field of characteristic 2, but it doesn't matter. So what we are trying to do is we are trying to come up with a function that gets two samples. These are x and y, written now in this FQ language. And it also is given a seed. And let me kill the suspension. The seed will be a field element. Okay. And it should output, again, an L tuple of FQ elements. Right, so x is going to come from here, y is going to come from here, and the seed is going to come from here. And now, written like that, the idea is kind of almost asking it to be there. The idea is, you can think of x, I mean, the way you wrote it, x is a point in the L-dimensional vector space over FQ, and y is also a point. So if x is uniform, then x is random, and then y looks at where x is and chooses where to be. But anyhow, it's a point. It's an adversarial point, but it's a point. And then what you're going to do, whenever you have 2 points, you should draw a line connecting them. And using the seed, you're going to sample a point on this line. So using S, and that's your output. So you're going to look at x and y, look at the line they span. You'll see in the proof that if x equals y, then no line is spanned, but that's actually even better. So don't worry about that. So assume x and y are distinct, when you look at this idea. And then you are going to look at the line connecting them, between them, the unique one, and then S is going to sample a random point from that line. So it will look something like that. So the merger on X, Y, and S is going to be, you can write it like that if you want. Right, so this line, parameterized by S, which is also the name for the seed, it goes for x and y, because when S is 0, you get x. When S is 1, you get y. And that's your output. That's the whole construction. It's like extremely beautiful. Okay, but let's analyze it. So we need to ask ourselves, how can we prove that this random variable is epsilon close to a random variable that has a lot of entropy, mean entropy? And, you can't work like that. There is a nice fact that makes it a more kind of operative definition than the definition that I just said. You're epsilon close to some source that has entropy. So here is a little fact. So any x, not our x. Let's call it maybe by a different name, z, any random variable z. Z is epsilon close to a random variable with mean entropy k, if and only if I'm going to cheat a little bit and say where I'm cheating for any set B, where z lives, say in 0, 1 to the n or fq to the l, but that's not too large, as large as this k, like 2 to that number, the probability that z is in B is at most epsilon. Right, so what I'm saying is that, being close to a high entropy source really means that you are not concentrated in small sets. Okay, so any set which is small, the probability that you will fall into it is not too large, and that's an if and only if. But you do lose a little bit in parameters, which I kind of omitted here. So this k maybe now may change a little bit in the different directions. You lose maybe a plus minus one, and also here maybe you lose a factor of two and so forth, really depending on the plus minus one that you're willing to lose here. But don't worry about it too much. If you want, you can put thetas and makes it all okay. Okay? But conceptually, that's what it is. So being close to a source with high entropy means that you don't fall into small sets too often. Yeah? And that's an operative definition. I mean, it's really easier to work with that now. Because what I have to do now is to understand why this thing never falls into a small set too often. Okay? So let me just write it down. So with this fact, which you can actually prove, it's not that difficult. As a hint, I'll tell you that in one direction is kind of almost trivial. In the other, you need to consider the set of heaviest element of your distribution. Okay, the elements that get the highest probability mass. You need to kind of truncate it in the right way and massage it a little bit, and you can prove this fact. It's actually not that completely easy, trivial, but it's doable. Anyhow, so with this fact, you can show that we need to show that. So we need to show that, well, the probability, for every B in FQ to the L, and I want to say that B is not too large. I really want to say this thing because I'm shooting for entropy 1 minus alpha n, but it's better to write it like that, which is the same because we're working over FQ, it's nicer to look like that. It's the same number, doesn't matter. The probability over S, X, and Y, over everything, that the merger, the merger, we know what it is, it's this, is in B, is at most epsilon. So, I mean, we need to prove this. I mean that in a sense that we need to choose Q such that this will hold. Okay? Q, by the way, we want to be small because log Q is the seed length, right? S is a field element, log Q bits is the seed. We want the seed to be short. Okay? So we need to argue that this thing holds. This thing holds. And if you look at that for a second, there is a good part and a bad part here. This is good because it's structured. Right? You made sure to construct a construction which is really nice, and you can argue about it. It's something linear in S. If you think of X and Y are fixed, it's linear in S and so forth. But this is bad. Right? This set B is an arbitrary set. I mean, it's a progress from working with the kind of more abstract definition of being close to a K-source, but still, I mean, it's an arbitrary set. I don't know. When you want to analyze something, you need everything to be structured, not half structured, half a mess, right? So what we are going to do is we're going to do the following. So think of this as FQ to the L, and you have this set B, which is really bad. So I'm drawing it like crazy. It's a crazy set, but it's not too large. So that's B. And we want to show that our random variable doesn't fall into B too often. So the idea will be to kind of put B in a nicer set, smoother set, something that we understand, potentially a bigger set. I mean, certainly a superset, but potentially bigger. And we are going to bound this, right? We are going to prove that this doesn't occur in our bigger set with that probability, let alone the probability of that element to be in B is, of course, smaller than epsilon. So that's the idea. We're going to lose in size, but gain in structure. Okay? Okay, so how does this work? So in order to do that, we are going to use what's known as the polynomial method, because our structure is going to be the zero set of a polynomial. So you have this set B. It's of size q to the 1 minus alpha L, as we said. And I don't like that set. So what I want to do is to kind of put it inside the zero set of a polynomial. Because polynomials are nicer to work with. We have results about them, Schwarz-Zippel. We know how they behave when you project them to a line, which we will use in a second, and so forth. So the idea is the following. Consider the subspace of all polynomials in L variables of total degree at most D. Right? So there's another parameter here on top of Q at most D. And so, as how many of those do we have? So it's roughly like n minus D choose n, which is definitely smaller than D over n to the n. I chose this bound because I know what will happen, and I know that D is going to be larger than n. Okay? So that's the best way to simplify this expression for me. Yeah, and I think n should be L. I can keep forgetting that. Yes. So it's L, L, and L, because you have L variables, not n. Okay. So, I'm not fixing a particular polynomial. I'm looking at the subspace of all polynomials of total degree at most D over FQ. I know that you have, sorry, not that many of them. That's the dimension of the subspace. This is the number of basis elements that you have, all monomials of degree at most D in the variables. And the point is that, what I want to do is to find a non-zero polynomial that vanishes over B. Right? If I'm going to find a non-zero polynomial that vanishes over B, then the zero set of that polynomial I can take to be B prime. Right? So B prime, which is a nicer but larger set, is going to be the zeros of some nice polynomial in this family. And okay. So, but in order to prove, and I don't want B prime to be everything, so I don't want Q to be the zero polynomial. I still want FQ to the L to be much larger than this. But the point is that I want to kind of wrap B in this nicer set. And so I need to prove the existence. I mean, it's all in the analysis. I don't need to find it, but I need to prove the existence of a polynomial that vanishes, a non-zero polynomial that vanishes over B. So if you think about it for a second, it's a linear algebraic problem. So if you give me any little b, every point in FQ to the L that happens to lie in B, then requiring that Q, so I'm thinking of Q as, has coefficients which are variables, are not fixed, coefficients to the standard basis as variables. So for every particular b, requiring that Q of B is 0, requiring that is a linear, like homogeneous linear constraint on Q's coefficients, right? So I'm considering a general degree D polynomial in the sense that I'm, the coefficients are variables, and every particular constraint, every little b, that constraint, it translates to a homogeneous linear constraint over the coefficients. It's highly nonlinear in terms of b, but it doesn't matter. We fixed b, and now over, considering the coefficients, we get a linear constraint. And we know, from linear algebra is that if the number of constraints, this is the number of constraints, is less, strictly less, than the number of, or than our lower bound, sorry, upper bound, on the number of, oh, it's a lower bound, sorry. Sorry, there are many dimensions. So if the number of constraints is smaller than our lower bound, definitely from the number of degrees of freedom that we have, then we know that there is such a Q which is non-zero, such that Q on B vanishes, right? Good. So let's make sure that this thing holds, and then we'll continue the analysis with this Q. And again, everything is in the analysis. I don't need the polynomial, like for the algorithm. So B, we said, is of size Q minus alpha L. And so this means that we need a Q to the 1 minus alpha to be less than D over L. That's one thing that we need. That's a requirement, okay? Moving forward, we are going to work with this Q. Okay, so now, as promised, we don't need to handle this B, we just need to bound the probability over S, X, and Y that S, or 1 minus SX plus SY, sorry, the whole point was not to do that. So we just need to bound the probability that 1 minus Sx plus Sy doesn't fall in the zero set of Q, or in other words, we just want to bound this, right? Because whenever this is in B, this happens, right? So bounding this larger event suffices to bound the probability that this thing, the output of the merger, is in B. Good. Okay, that's now doable. That's the problem about like polynomials. Everything is clean now, right? So, there are two adversaries here. There is the adversary Y, which follows your X, and there is the adversary Q, which is, you need to work for every subset B by the definition of, by this fact that we work with instead of working with the actual definition of being close to a k-source. So that B induces a Q. So now what happened, and that always happens in pseudo-randomness, is that you reduce the power of the adversary to something manageable. So now the adversary has this Y and this Q. So you need to work for every Y and Q, or Y and B, and therefore Y and Q. And the first thing we need to observe is that, I mean, it's an easy fact, is that we can assume that Y is a deterministic function of X. Okay, because I mean, it could have like its own randomness. It can do things. It can look at, it can toss a coin and decide whether the fourth bit of Y equals the, majority of the, second or third or whatever bits of X and so forth. But it never helps because, if you know how to handle deterministic functions of X, then any randomized function of X is just a convex combination of those. And you can immediately show just by the definition of the merger that once your merger works for two functions, it works for the convex combination and for any number of functions, therefore. So the first thing is that it suffices to consider Y as a function of X. So let me change it here. So I write it as little y as a function of capital X, okay? And I'm removing this here. Okay, so now what happened is that we fixed, now in terms of randomness, we fixed Y. I mean, S and X are the only things that are alive now. And the second thing we're going to do is we are going to fix the X. So, the proof is going to be by contradiction. So let's assume by contradiction that, and then I'm going to run the the reverse thing of that. So over all S and X, Q of 1 minus S, X plus S times little y of X is 0, is at least epsilon. Now, what I'm claiming, and it requires a little bit of thought, is that this means that if this happens, then for epsilon over 2 fraction of x's, let me take this to the, okay. Let's take it to the following page. So for epsilon over 2 fraction of the x's, we have that the probability over s alone of q of 1 minus s little x plus s y of little y of little x equals 0 is at least epsilon over 2. Right, so what I'm saying is that if this happens with probability at least epsilon over s and x, then there must be at least, epsilon, for at least epsilon over 2 fraction of the x's, it must be the case that when you now go over all s's, you get at least epsilon over 2. Right, because if less than epsilon over 2 fraction of the x's will meet this, then you won't have enough to get a total of epsilon, right? Because if P of the x's satisfies that, right, then it's always confusing. Then, yeah, okay, it's something that you can show. Because the rest of the, what you do is that, so if P of them, okay, if this is P, just to make sure that we're not, I don't want to mystify it too much, it's really simple, but if this function is P, which I want to show it's at least over 2, that you know that P could get you 1, because P fraction of the epsilon are larger than epsilon over 2, but the rest can get you at most epsilon over 2. And you know that this is at least epsilon by the assumption here, or larger than epsilon. So from here you can see that P must be at least epsilon over 2. Right? You can just move things around, even slightly larger, but never mind. Okay? Never mind that, it's not really important. I'm just going to erase it. Okay, so what's good in that? So now we are kind of fixed the dependency on y and x, and then we fixed x, and now we just, there are going to be many x's that will work, but we fix x, and now we are looking at this expression. And we ask ourselves, what's the probability for this to happen? And the point is that now we're looking at something really nice. So Q is a multivariate polynomial, but what you do is you restrict it to a line, right? X and yx are fixed. So this is a line. So this becomes a univariate polynomial. All right, so this polynomial, all the way here, this is a univariate polynomial. You can call it by names like Q sub x or something, okay? But it's a polynomial in fq to the s. Right? Polynomial only in s, fq to the s, because x and y are fixed. And what do you know? You know that it tends to be 0 quite a lot, this polynomial. And the second thing you know, it's the degree of this polynomial is at most d, right? Because the total degree of q was at most d, and therefore when you restrict it to a line, you get degree at most d. So the degree of q sub x is at most d, but the number of zeros of q sub x is at least epsilon over 2 or larger even times q, right? Because s is uniform over fq, and epsilon over 2 fraction translates to epsilon over 2 times q zeros of this polynomial. So if we are going to choose the parameters such that d is smaller than the number of zeros, so that's something that we'll choose, then we get that q sub x is the zero polynomial. Right? That's the cool thing about polynomials. If they are they, move over some threshold of zeros when they are just the zero polynomial. You can't be like, you can't have any number of zeros. There is like a sharp threshold there. And that's great because this means, in particular, that qx of 0 is 0. I mean, the entire polynomial is 0. But qx of 0 is x. I mean, is q of x. Without the subset, just q of x, right? From here. So to summarize, we know that every of these many points x's, any kind of good point, because of this argument, is a zero of the multivariate polynomial q. Right? I mean, the way we did it was to, the way we proved that was to restrict q to the line, make sure that we chose the degree of q, and therefore the degree of the resulting univariate polynomial is too small to have that many zeros without being a zero as a polynomial. Therefore, the polynomial is a zero polynomial, kind of this projected polynomial is a zero polynomial. And so, apply when you evaluate it at zero, you get zero. But evaluating that univariate polynomial at zero means evaluating the original polynomial at x, little x. Okay, but now we got many zeros, right? So now we know that therefore q has epsilon over 2 fraction of zeros in fq to the L, right? Because every x like that is a zero of q. But if we choose the parameters correctly, and actually we don't need to because it's happened to be what we chose here, and this will contradict the Schwarzschild lemma, right? Because by Schwarzschild, we know that number of zeros of q, I mean, it's a non-zero polynomial, q. So the number of zeros is at most d over q times q to the L. That's Schwarzschild. And we just proved that it has many zeros. Epsilon over 2 times q to the L. And that's a contradiction to this choice of parameters. Good. That's it. Now we just need to see what we got. So, I mean, we proved what we needed to prove. We just need to make sure uh, that there is nothing cyclic about it, and we can choose parameters that are fine. So the two requirements that we had were this one, like twice, both here and here, but it happens to be the same, and that one. Q to the 1 minus alpha is at most d over L. Okay, so we need to make sure these two holds, and we are all kind of going up. We'll just do it with equalities and remove the twos because again we live once. So plugging this here will get you epsilon q over L. I mean, I don't like t. This is a parameter that we introduced. At least q has something to do with the seed length. These are some parameters, so I'm just substituting d here. And then you'll see that the q cancels out, like the minus alpha stays, but the q cancels out. So what you get is that q to the alpha is L over epsilon. Therefore, q is L over epsilon to 1 over alpha, which, it's roughly the same, but it's definitely smaller than n over epsilon to 1 over alpha, because L was n over log q. And that's it. That means that the seed length is 1 over alpha times log n over epsilon, as promised.